Once again, we're going to use Stokes Theorem to evaluate the line integral over c of f dot dr, which means that we won't actually do that. We're going to use a double integral. Our vector field is f of xyz is equal to 2yi plus xcj plus x plus yk. C is going to be the curve of intersection of the plane z is equal to y plus 2, and the cylinder x squared plus y squared equals 1. Now folks, if we were computing the line integral over c of f dot dr directly, then we would need a parameterization for the curve of intersection. But we're going to use Stokes Theorem, which means that we're actually going to find the surface integral over s of the curl of f dot ds. Let's see what this surface looks like. I've drawn here the plane z is equal to y plus 2, as well as the cylinder x squared plus y squared equals 1. Notice that my orientation is a little bit different because I wanted to be able to see the slope of the line z equals y plus 2 in the yz plane. The surface S that we're talking about here is the portion of the plane that is contained within the cylinder. So S is that angled top surface. C is, of course, the actual curve of intersection between the plane and the cylinder. But what we're actually going to use is the trace of that boundary in the xy plane. Ultimately, it is that region that will be our region D. You can verify that the curl of f will be 1 minus x, negative 1, z minus 2, and ds, because s is a portion of a plane, is going to have the vector 0, negative 1, 1 times dA. This gives us that the curl of f dot ds is equal to, almost wrote that as a vector, 0 times 1 minus x, negative 1 times negative 1 is 1, and 1 times z minus 2 is plus z minus 2. However, since our region D is in the xy plane, we want this in terms of x and y and not in terms of z. So we're going to look and we see that z is equal to y plus 2. Therefore, we end up with y plus 1 when we substitute and simplify. So the line integral over c of f dot dr, which is what we were asked to compute using Stokes theorem, is the surface integral over s of the curl of f dot ds, which is going to be the double integral. Our integrand is y plus 1 dA, and our region D is a disk of radius 1. If you sensed we were going to polar coordinates, you were right. We're going to go from 0 to 2 pi. That disk of radius 1 gives us a radius from 0 to 1. Y is equal to r times the sine of theta. Then we have our plus 1, and dA is r dr d theta. Distributing and integrating with respect to r is going, and then substituting, I suppose, is going to give us 1/2 plus 1/3 times the sine of theta d theta, which then gives us 1/2 theta minus 1/3 times the cosine of theta from 0 to 2 pi. We end up with a result of pi.